Welcome! Today, we'll be exploring an interesting problem from LeetCode, problem number 2105, Watering Plants 2. This problem challenges us to simulate two gardeners, Alice and Bob, working together to efficiently water a row of plants. We'll discuss the problem, explore potential solutions, and analyze their complexities. Let's dive in. In this problem, we have two gardeners, Alice and Bob, who are tasked with watering a row of plants. The plants are arranged in a straight line, and each plant has a specific water requirement, which is represented by an array called plants. For example, if plants I equals 3, it means the ith plant requires 3 liters of water to be fully watered. Alice starts at the leftmost end of the row, at index 0, and moves to the right, while Bob starts at the rightmost end, at index n1, and moves to the left. Both gardeners have their own watering cans, with Alice's can initially holding capacity A liters and Bob's can holding capacity B liters. However, if either gardener runs out of water while watering a plant, they must return to their starting position to refill their can before they can continue. Importantly, Alice and Bob only water the plants on their respective sides, and they stop moving once they meet in the middle. Your goal is to calculate the total number of refills required by both Alice and Bob combined to water all the plants in the row. The problem requires us to consider the initial capacities of the watering cans. Alice starts with capacity A liters, while Bob starts with capacity B liters. These values determine how many plants each of them can water before needing to refill. The output of the problem is a single integer that represents the total number of refills required by both Alice and Bob. To better understand the problem, let's look at a few examples. In the first example, the input array plants is 2, 4, 5, 1, 2, and the initial capacities are capacity A equal to 5 and capacity B equal to 7. The expected output is 1, representing the total number of refills required. Here's the explanation for the first example. Alice starts with a capacity of 5 liters. She begins watering from the left, so she waters the first plant, which requires 2 liters, leaving her with 3 liters. She then moves to the second plant, which requires 4 liters. Since she doesn't have enough water left, she has to return to her starting position to refill her can before continuing. Meanwhile, Bob starts with a capacity of 7 liters and begins watering from the right. He waters the last 2 plants, which require 2 and 1 liters respectively, and still has water left in his can, so he doesn't need to refill. In total, only Alice needs to refill her can once, resulting in 1 refill. Now, let's consider another example where plants equals 2, 2, 3, 3, capacity A is 3, and capacity B is 4. In this case, Alice starts with 3 liters and waters the first plant, which requires 2 liters, leaving her with 1 liter. When she reaches the second plant, which also requires 2 liters, she doesn't have enough water left, so she must return to refill her can. Bob, on the other hand, starts with 4 liters and waters the last 2 plants. He waters the third plant, which requires 3 liters, leaving him with 1 liter. However, the last plant also requires 3 liters, so Bob must refill his can as well. This means both Alice and Bob need to refill their cans once, resulting in a total of 2 refills. Finally, let's look at a simpler example. If plants equals 5, and both capacity A and capacity B are greater than or equal to 5, such as 10 and 8 respectively, then no refills are needed. Either Alice or Bob can water the single plant without running out of water. This example highlights an edge case where there is only 1 plant, making the problem straightforward. Additionally, we must consider other edge cases, such as when plant water requirements exceed both capacity A and capacity B, leading to frequent refills, or when the capacities are very large, resulting in fewer refills. Another scenario to consider is when Alice and Bob meet near the middle, where their progress determines which plants they water. These constraints and edge cases ensure that the solution we craft is comprehensive and efficient for all possible inputs. To solve LeetCode problem number 2105, we need to simulate the actions of two gardeners, Alice and Bob, as they water a linear row of plants. Each plant has a specific water requirement, and both gardeners have fixed water carrying capacities. Alice starts watering from the left side of the row, while Bob begins from the right. One approach we can consider is the brute force method. In this approach, we simulate every step taken by both Alice and Bob as they move toward the center. Each gardener waters the plants in their respective direction, decrementing their water capacity as they go. If a gardener's capacity becomes insufficient to water the next plant, they must return to the river to refill their can, and we track the total number of refills for both. While this method has the advantage of simplicity and runs in O(n) time, as each plant is visited exactly once, it does not exploit any symmetry in the problem or optimize the process. This makes it less suitable for larger inputs, as it performs redundant computations and lacks scalability. Another approach we can use is the optimized greedy method, which improves on the brute force solution by reducing redundant computations and taking advantage of the problem's inherent symmetry. In this approach, Alice and Bob continue watering plants in their respective directions until they meet or cross paths. Each gardener operates independently, refilling their can only when necessary. Key observations here include the fact that Alice and Bob never water the same plant, and their refill counts are calculated separately. The sum of their refill counts gives the total number of refills needed to water all the plants. This method is efficient, as it processes each plant only once, resulting in O(n) time complexity. Additionally, it avoids any unnecessary checks and does not use extra space, maintaining O(1) space complexity. The trade-off here is that this approach prioritizes simplicity and efficiency over exploring more complex strategies, but it is well suited for the problem's requirements. The optimized greedy approach was ultimately chosen because it offers the best balance between simplicity and efficiency. By directly simulating the problem and leveraging the independence between Alice and Bob, this method minimizes redundant calculations and computes the total refill count in linear time. Its O(n) time complexity ensures that it can handle large inputs up to 10,000 plants effectively. Additionally, its O(1) space complexity means no extra memory is used, which keeps the solution lean and scalable. Compared to the brute force method, the optimized approach is clearer and better equipped to handle edge cases, such as uneven water requirements for the plants or varying refill needs for the gardeners. Advanced methods, like dynamic programming, are unnecessary here because the problem's requirements are efficiently met with this greedy approach. In conclusion, this strategy achieves the goal of clarity, efficiency, and practicality, making it the optimal solution for this problem. To solve this problem, we need to simulate the actions of two gardeners, Alice and Bob, as they water plants arranged in a straight line. Alice starts on the left side, while Bob starts on the right. Each plant has a specific water requirement, and both Alice and Bob carry a limited amount of water. If they run out of water while watering the plants, they need to return to their starting point to refill. Our goal is to calculate the total number of steps taken by both gardeners combined to water all the plants. To achieve this, we begin by initializing several key variables. First, we define two pointers, left to represent Alice's position at the start of the array, and right to represent Bob's position at the end. Next, we set up two variables, Alice_water and Bob_water, to track how much water each gardener has left, initializing them to their respective capacities. Lastly, we initialize a steps variable to accumulate the total steps taken throughout the process. Now, we simulate the watering process based on the positions of Alice and Bob. As long as Alice's pointer left does not surpass Bob's pointer right, both gardeners will continue working in parallel. For Alice, if she has enough water to handle the current planted plants, left, she waters it, reduces her water by the required amount, and moves to the next plant by incrementing left. However, if her remaining water is insufficient, she must return to her starting point to refill. This requires adding twice the distance back to the start, which is 2 left 0, to the total steps. After refilling, her water supply is reset to full capacity. Similarly, Bob checks whether his remaining water is sufficient to water the planted plants, right? If so, he waters it, reduces his water accordingly, and moves closer to Alice by decrementing right. If his water runs out, he must return to his starting position, adding 2 and 1 right to the steps, and resetting his water. Both Alice and Bob perform these actions independently, and their positions and step counts are updated in parallel. When Alice and Bob eventually meet at the same plant, which happens when left equals right, we need to decide which of the two will water it. Only one of them needs to handle this plant, so we check whose remaining water is sufficient. If Alice can water the plant, she does so, and we increment the total steps by 1. Otherwise, Bob waters the plant, and the steps are increments similarly. At this point, all plants will have been watered. Finally, after processing all plants, the value stored in the steps variable represents the total number of steps taken by Alice and Bob combined. This approach ensures that every movement, whether forward or back to refill, is accurately accounted for. Key insights here include the independence of Alice's and Bob's actions due to the two-pointer strategy, as well as the importance of efficiently managing water refills to minimize extra steps. By carefully simulating each step, we achieve an efficient O(n) solution, even when accounting for edge cases like when Alice and Bob meet. To implement this solution, we rely on a few simple data structures and variables. The plant's array stores the water requirements for each plant. Two pointers, left and right, are used to track Alice and Bob's positions as they move inward from their respective starting points. Additional variables, Alice_water and Bob_water, keep track of their remaining water, while the steps variable accumulates the total steps taken. From a performance perspective, the algorithm is highly efficient. The time complexity is O(n), as we process each plant exactly once using the two-pointer approach. The space complexity is O(1), since we only use a few variables and do not require any additional data structures beyond the input array. This makes the solution not only fast but also memory efficient, ideal for handling larger input sizes. To better understand how the algorithm works, let's go through an example step by step. Suppose the input is plants equals 2, 4, 5, 1, 2, with Alice's capacity A, set to 5 and Bob's capacity B, set to 7. Initially, Alice starts at index 0, and Bob starts at index 4. Alice waters the first plant, which requires 2 units of water, leaving her with 3 units. She then moves to the next plant. Bob, on the other hand, starts with the last plant, which also requires 2 units. After watering it, he has 5 units left and moves inward. Next, Alice reaches plant 1, which needs 4 units. Since her remaining water is insufficient, she returns to refill, adding 2 steps for the round trip and 1 step to move forward again. Meanwhile, Bob waters plant 3, which needs 1 unit, and moves closer to the center. Finally, both meet at plant 2, which requires 5 units. Bob has enough water to handle it, so he does, and the total steps are tallied. By following this process, we calculate the total steps taken as 14. This example highlights how the algorithm efficiently handles both regular and edge cases while minimizing redundant computations. Here, we start by defining the minimum refill method in the solution class. The inputs are the list of plants, Alice's watering can capacity, and Bob's watering can capacity. First, we calculate the number of plants, stored in n, and initialize 2 pointers, left starting at the first plant and right at the last plant. We also set up variables to track the current water levels for Alice and Bob, as well as a counter, refills, to count the number of refills needed. The while loop runs as long as the 2 pointers have not crossed. If both pointers meet at the same plant, meaning Alice and Bob arrive at the same position, we decide who should water the plant by comparing their remaining water levels. If Alice has more or equal water, she handles it, otherwise, Bob waters the plant. In either case, if their water level is insufficient, they refill their cans, and we increment the refills counter. After watering, their respective water levels are reduced by the amount the plant requires, and we break out of the loop since we've handled the last plant at this point. Now, for the general case when Alice is watering the plant at the left index, if her water level is less than the plant's requirement, she refills her can, and we increment the refills counter. Once she has enough water, she waters the plant, and her water level decreases accordingly. Next, we move the left pointer to the next plant and handle Bob's turn at the right index. Similar to Alice, if Bob's remaining water is less than the plant's requirement, he refills his can, which increases the refills counter. Once he has enough water, he waters the plant, and his water level decreases by the amount needed. After this, we decrement the right pointer to move to the next plant on his side. The loop continues until all plants are watered, with Alice and Bob working from opposite ends of the row. Once the loop ends, the total number of refills needed is returned. This approach ensures that we efficiently determine the minimum number of refills while keeping track of both Alice's and Bob's actions as they water the plants from their respective sides. Here, we define a class-named solution and implement a method called minimum refill. This method takes three parameters, an array of integers called plants, representing the water requirements for each plant, and two integers, capacity A and capacity B, which represent the initial water capacities of Alice and Bob respectively. The goal is to calculate the minimum number of refills required to water all the plants. We start by initializing some variables. The length of the plant's array is stored in n, and we set 2 pointers, left and right, to the beginning and end of the array. Alice and Bob's initial water capacities are stored in Alice water and Bob water, and a counter for the number of refills is initialized to 0. Next, we enter a while loop that continues as long as the left pointer does not exceed the right. Inside the loop, we first check if Alice and Bob meet at the same plant by comparing left and right. If they do, we decide who should water the plant based on whose remaining capacity is greater. If Alice's water is insufficient for the plant, she refills, increasing the refill counter, and then waters the plant. Similarly, if Bob is the one watering, and his water is insufficient, he refills before watering the plant. Once this is handled, the loop breaks since both pointers meet at the same plant. Now, outside of the condition where Alice and Bob meet, we handle the general case where they water plants from opposite ends of the array. Alice starts by watering the plant at the left pointer. If her remaining water is less than the plant's requirement, she refills, increments the refill counter, and resets her water to its full capacity before watering the plant. After this, we move the left pointer forward. Similarly, Bob waters the plant at the right pointer. If his remaining water is insufficient, he refills, increments the counter, and resets his water to its full capacity before watering the plant. Afterward, the right pointer is moved backward. This process continues until the 2 pointers overlap or cross. Finally, once all plants are watered, the method returns the total number of refills required. This approach ensures that both Alice and Bob efficiently water the plants while minimizing the number of refills. In this example, we are given plants equals 2, 4, 5, 1, with Alice starting at the leftmost plant and Bob at the rightmost plant. Alice has a water capacity of 6, and Bob has a capacity of 5. Both start with no refills. Initially, Alice waters the first plant, which requires 2 units of water, leaving her with 4 units. At the same time, Bob waters the last plant, which needs 1 unit, leaving him with 4 units as well. After watering, Alice moves to the second plant, and Bob moves to the third. Alice now waters the second plant, which requires 4 units, depleting her water completely. Meanwhile, Bob attempts to water the third plant, which needs 5 units, but his remaining water isn't sufficient. He refills his can, which counts as 1 refill, and waters the plant, depleting his water again in the process. At this point, the pointers for Alice and Bob overlap, and the process is complete. The total number of refills required is 1. By the end of the first example, we see that Alice and Bob managed to water all the plants with only 1 refill required. This gives us the output of 1. Now, we move to the second example, where plants equals 2, 2, 3, 3, and both Alice and Bob start with a capacity of 3. As before, they begin on opposite ends of the row of plants, and the count of refills starts at 0. Here, Alice first waters the leftmost plant, which requires 2 units, leaving her with 1 unit. Bob starts from the rightmost plant, which needs 3 units. Since he doesn't have enough water, he refills once, bringing the refill count to 1. After refilling, he waters the plant, using all his water. Next, Alice moves to the second plant, which also requires 2 units. She doesn't have enough water, so she refills, making the total refills 2. She then waters the plant, leaving her with 1 unit. Bob moves to the third plant, which requires 3 units. Again, he refills, increasing the refill count to 3, and then waters the plant. At this point, all plants are watered, and the total number of refills is 3. In this third example, the plants have uniform water requirements, with each needing 1 unit. Alice and Bob each have a capacity of 2, so they both start with enough water to handle 2 plants without refilling. Alice waters the first plant, using 1 unit and leaving her with 1 unit. Bob waters the last plant, also using 1 unit and leaving him with 1 unit. They then move inward, where Alice waters the second plant, depleting her water to 0, and Bob waters the third, also depleting his water to 0. Since all plants have been watered and neither Alice nor Bob needed to refill, the total refills remain at 0. At the end of this example, Alice and Bob successfully water all the plants without requiring any refills. This results in a total refill count of 0, and the output for this example is 0. This demonstrates an efficient scenario where both Alice and Bob have sufficient capacity to manage the row of plants without interruptions. The time complexity of this solution is O(n), where n represents the number of plants in the array. This efficiency comes from the use of two pointers, left and right, which traverse the array inward from both ends. Each pointer processes one plant at a time, either moving closer to the center or stopping when both pointers converge. It's important to note that every plant is visited exactly once, and no plant is revisited. For each plant, the operations like checking water capacity, refilling, and updating variables are all O(1), meaning they take constant time. Since the loop runs at most n times, the overall time complexity is linear, or O(n). Whether we analyze the best, average, or worst case, the result is the same. Even in the best case, when no refilling is required and each plant needs less water than the initial capacities, the algorithm still iterates through all the plants once. Similarly, in the worst case, even if every plant demands a refill, the number of iterations remains the same because each plant is processed exactly once. This consistent performance across best, average, and worst cases ensures that the algorithm is highly efficient in terms of time complexity. The space complexity of this solution is O(1), meaning it uses a constant amount of extra memory regardless of the size of the input. This efficiency comes from the fact that the algorithm only relies on simple variables like left, right, Alice_water, Bob_water, and refills, all of which occupy fixed memory. No additional data structures are created, and the input array plants is accessed directly without any modification. Because the memory usage does not increase with the number of plants, the space complexity remains constant. When comparing this optimized approach to a brute force or naive method, the differences become clear. A less efficient solution might involve multiple passes over the array or unnecessary data structures to simulate the watering process, potentially increasing both time and space requirements. For instance, a naive method might simulate the entire process for Alice and Bob individually, leading to redundant calculations and a possible time complexity of O(n²). In contrast, the current solution achieves the optimal O(n) time complexity by ensuring that each plant is only visited once, and it maintains O(1) space usage by avoiding the allocation of unnecessary memory. To mathematically prove the big O notation, let's consider an array of n plants. The condition for the while loop is left equals right, and in every iteration, either left is increment or right is decrement. This means that the loop executes at most n iterations, as both pointers progress toward each other from opposite ends of the array. Within each iteration, only constant time operations are performed. These include comparisons, arithmetic operations, and pointer updates, all of which take O(1) time. Since the total amount of work done is directly proportional to the number of plants, the time complexity is O(n). Additionally, because the algorithm does not use any additional memory beyond a few fixed variables, the space complexity remains O(1). Together, these characteristics demonstrate that the solution is both time and space efficient, with linear time complexity and constant space complexity. When tackling this problem, there are a few common mistakes to be mindful of. First, not resetting Alice or Bob's watering capacity when they return to the river is a frequent error. The problem explicitly states that each gardener refills to full capacity at the river, so failing to do this leads to incorrect calculations. Second, incorrect boundary handling can cause issues. For instance, if Alice and Bob meet at the same plant or if the number of plants is odd, it's easy to double count or skip a plant. Lastly, assuming that both gardeners will always water an equal number of plants is another pitfall. Water requirements vary across plants, and depending on their capacities and starting positions, one gardener might end up watering significantly more than the other. Understanding these nuances is key to avoiding errors. Another common pitfall is inefficient simulation. This happens when you use redundant loops or recalculate values unnecessarily, which increases the time complexity of your solution. A more efficient approach ensures that each plant is processed in just one pass. Hard-coding values is another mistake to avoid. For example, hard-coding specific watering capacities or plant positions might work for certain test cases but fails for dynamic inputs. Always write solutions that generalize well to all scenarios, ensuring robustness and flexibility. When solving this problem in an interview, it's important to focus on collaboration. Many two-pointer problems, like this one, require a clear explanation of how the two agents Alice and Bob divide their tasks. Be ready to justify your approach to splitting the work. Additionally, discussing edge cases is crucial. For example, consider scenarios where the row of plants is empty, there's only one plant, or the water capacities are too small to fully water any given plant. Interviewers also appreciate discussions on optimization, so highlight how your solution minimizes passes through the array and avoids redundant calculations. If you're asked to suggest alternative approaches, make sure to explain their trade-offs in terms of complexity and practicality. This shows your ability to evaluate and adapt solutions effectively. To further your understanding of two-pointer problems, you can explore related problems on LeetCode. For instance, problem 1021, remove outermost parentheses, involves a similar simulation with careful boundary handling. Problem 167, 2sum2, is another classic two-pointer problem that focuses on collaboration between two agents. Additionally, problem 11, container with most water, requires optimizing a shared task using two pointers. Finally, problem 1769, minimum number of operations to move all balls to each box, involves simulating movement and minimizing costs. As for alternative approaches to solving this problem, one option is to simulate each gardener independently by using separate loops to calculate their total steps. While this is easy to implement, it's less efficient due to redundant calculations. Another option is a recursive approach, which may appear elegant but is less practical for larger inputs because of potential stack overflow and additional overhead. Dynamic programming, or DP, can also be considered as an alternative approach. Using DP, you can store the minimum steps required for each gardener to water up to a certain plant. This approach, however, is more complex to implement and might be unnecessary for this problem, as the greedy approach already provides an efficient solution. While DP can sometimes offer more structured solutions for problems with overlapping subproblems, in this case, it introduces additional complexity without offering significant benefits over the simpler greedy strategy. Therefore, it's important to assess whether the added complexity is justified for the problem at hand. Great job! To recap, we explored the watering plants 2 problem, discussed an efficient solution, and highlighted key concepts like task division and simulation. Keep practicing and applying these strategies to similar problems. Thanks for watching, and don't forget to like, share, and subscribe for more coding solutions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!